With everything in place, the modal analysis basically is to utilize the orthogonality properties of the matrix and to help us to solve the multiple degree freedom vibration system. And this is a very powerful method, and these methods can be used for free vibrations, can be used for forced vibrations. And with this approach, we're going to integrate everything we have learned from chapter 1 to chapter 4. Everything will be applied to here. So let me get that ready, and I'm going to still stick with the same examples, but before we do it, and I will try is do two ways. One side is symbolic, the other side is numeric. Okay, so let me start with the equations of motions. Equation of motions in general descriptions is like this. Okay, and for general situations, let me assume this is under the force. Okay, so basically, if you like to expand it, this will be something like this: M1, M2, and for example, we have a numbers and numbers here, and X1 and Q, Xn double dot. And K basically is the K11, K22, and KNN. So that is the K12, etc. So basically this is symmetric matrix. Okay. And for the force, that can be F1T. And FNT. Okay. And here we consider the initial conditions. Initial conditions, for example, X and this one. Okay. So that means initial conditions we have given is we know the X 0 basically is X1, 0, and Xn, 0, and then velocity arranged in this form. Okay, given. So that is a statement of the progress. And then we see how can we utilize these things to decouple. And this system is called a coupled. This is called the coupled differential equations. Again, here this is the matrix form representing n set of the linear differential equations. The coupled equation is due to the K matrix. This is not diagonal matrix. Okay, the coupled. Again, if you here, let me make a scratch note. If you expand the first equation, that is M1 times X1 double dot plus K1 times X1, K12 times X2, etc. So when you expand this row, multiply with this column, that not only X1 appeared in the first equation, but remaining other parameters, the variables will be appear. So that makes things makes things coupled. Our goal is to decouple such differential equations. So what we would do is this: the modal analysis start with we play around, and here use colors to denote. And the step 1 is this: we realize the general solutions the solutions. The solutions is linear combinations of the modal vectors. Okay. And for this example, let me see. If you remember our lecture notes, and that one is C1 cosine omega t, omega 1t plus B1. And for example, for our modal vectors, point 2673 and point 5345. In your lecture notes, and that happened before they normalized, and if you still have that one in place, I think these vectors I used in that lecture is 1, 2. Right? If you turn over your notes back to Friday's last week. Okay. And then this one, D1 cosine omega qt plus dq, and for these vectors minus 9.8452. Okay, so that is what I mean, the linear combinations. And in terms of the linear combinations, you can see this is the time-dependent coefficients of the linear combinations, right? Okay, so that is what we have done before. And usually we not to write so much, so usually we simply use a simple notation using Q1t and Q2t to represent the time-dependent linear coefficients for linear combinations. And this one, let me use this notation x1, and here I have utilized the normalized, okay? So this is x2. So with these examples, we can copy, and then actually our notations is this. The general xt is x1, 2, 3, 4, etc. And that one is q1 and x1 plus until the q. And here we have n degree freedoms. So we have the n modal vectors. Okay, so it is a function of no arrows. Okay, so compared to our numeric, and that is the way we try to set up the problem like this. And in common terms, the people give the name of the Q1, Q2 is called the generalized coordinate. Okay, and such a coordinate is described compared to x1 and x2. Here we just simply call the degree of freedoms in Cartesian coordinate system, and here we call it generalized. And there's a story behind, but because I skip off the Lagrange equations, so you just memorize. Okay, that's called the generalized coordinates. Okay, so here for n degree freedom systems, we have the n numbers of the generalized coordinates to be used in modal analysis. Okay, and in precise way we can write into Q. So basically, this is the Q1 times this and Q2 times that one can be written by this. So that is. This is I'm going to write into matrix form. So that's the two numbers. This one multiplied with this one. So that is given to this. And then the second vectors is x2 and multiplied with q2. So basically here we rearrange. So this one multiplied with this one is basically equal to these equations here. Okay. So I write into the matrix form like this. Okay. The arrangement again, you put the first modal matrix as a column vector into the first column, and this is the second modal vectors. From here you can clearly see the contents. Okay. And Q1, Q2 again arranged in this way. So here we can put into this. So that is basically is a modal matrix, and let me write one more time. So basically that is the first modal matrix and the nth modal matrix. Okay. And then multiply with Q1, QA. Okay, so again here the arrangement is for each modal vector that is a column vectors. Okay, you place each of the column vectors to fill up into an n by n matrix. Be good? Yes.
So looking at that equation, basically in blue, you could say that to write one equation of motion, you just use the top number of what's in the, just looking at the blue.
Okay.
And using the top number from each one of those, that would be one modal vibration
Yes.
equation, and the next one would be the second modal vibration equation. Is that correct?
Say that again.
You would just use the top number in that vector, and that equation would be one mode of vibration equation, and then the bottom would be the next mode of vibration equation.
So the solution basically is x1t and x2t.
Okay.
So for x1, that is whatever this number multiplied with this, plus this one with that one.
Okay, cool.
Second mode is with a different component, but they have the same generalized coordinates. Good?
Yeah.
Okay. So that's the reason this one defined as a motion, because that it tells the relations between x1 and x2 in each vibrations. Okay. Okay, now we're back to here. So this one, basically, we can take into our definitions of the modal matrix. This one can be written by this. And here we simply define this is the column vectors of the generalized coordinate systems. Okay, so this is an important step for any general solutions. We can express in terms of the modal matrix and then utilize the generalized the coordinate system like this. Okay. So keep this one in mind. I'm going to begin to proceed the very important steps and for the solution process. So we have this one. Again, this simply is saying the general solution is a linear combinations of the modal matrix. Okay, and that statement basically can be written by this. Okay, keep this format in mind. Okay. And so now with this one, then I'm going to introduce the x into the equation of motions. So therefore, the equations of motions can become, and I simply replace the x with this one. So look at this carefully. So m, okay, and we are given is x equal to capital X times Q. Okay, so therefore double dot equal to double dot here. Okay, so that means the x double dot is replaced by this one, so that is capital X, the modal matrix, and Q double dot. You good? Okay, and now we go to the K. And for this one equal to capital X times this Q. Okay, so this one becomes this one. And Good? Okay, and the F is the same, so keep writing F. And the same initial conditions. Good? Okay, so now come to the very magic step. You see, with this one in mind, and then we have such a good formula. If I want to utilize the two formulas here, we need additional manipulations. So here the additional manipulation to have the two quantities appear in these equations, what manipulation we can do. So let me highlight the two terms basically appear here, and the K matrix, the two terms appear here. So can you see if we pre-multiply the whole equations with something, let me call this is equation 1 by this. Okay, so let me write out here. So that is capital transpose M Okay, so here I simply pre-multiply is with this one. So for every single terms, I have this term. Pre-multiply, that means multiply that one at the front, called the pre, okay? So you can see here, that is basically scaling of this equation to here. Be good? Okay, and I wait for you to finish the writing of these equations. Good? Okay. And once you finish, then get rid of the unnecessary notations. So utilize these properties. If X the model vectors are, I would say, for normalized vectors that are normalized with respect to matrix N. So that means the two properties satisfied. So therefore, these terms will become 1, 1, and 0, 0. And for these terms, it will become omega 1 squared, omega 2 squared, 0, 0, and omega n squared, 0. You good? Okay, for model vector that is normalized, then the two here I will accordingly apply that information to here. Let me write it up in a good way. And let me define this one. So whatever this one, let me define that is called the, let me simply define this is called the Q vectors, okay? So transpose of X matrix multiply what with whatever F, I define as a Q. And if I write it up into the symbol Q1T and QNT, like this one. Okay, so in this way, we keep this one in mind, then the whole set of the equations, So that means here, let me call this equation 2, this one, okay? So therefore, equation 2 becomes 1, 0, 0, 1, 1. Basically it's 0. Q1, Qn, T. Plus omega 1 square, omega 2 square, omega n square, and 0, 0. Q1, Qn equal to Q1 T, Qn T. I'm running out of the space here. Okay. So the original coupled equation of motion becomes this. And let me expand one more time. So this one basically is the matrix representations of n set of linear differential equations. Right now, such the linear differential equations, let me expand it. Basically, that is the first row multiplied with this plus the first row multiplied with this. So that means representing is this Q1 double dot T plus omega 1 square. Let me ignore the function of T. So Q1 plus omega 1 square Q1 equal to Q1 T. Okay, I think that's the function of time. Okay, and then the second equation is Q2 double dot function of time plus omega 2 square Q2. Then the last equation is this. Right? So what is the advantage of this? The original coupled differential equations right now decoupled. They decoupled into an n set of linear order differential equations. Right? Be good? Everyone get it? Then we can see our equations, our problem here. So let me do this one. So for our numeric, basically is this xt is equal to 0.2653. Okay, so therefore we're plugging into information here. This is our modal matrix, and this is our generalized order space. Okay, so we introduce of motions, okay, like this. So basically that becomes m capital X and Q double dot plus K X and Q and equal to 0 here. Okay, so here we pre-multiply, and so here we pre-multiply. That means the capital transpose and capital transpose here. Okay, so basically this one becomes 1, 0, 0, 1 and Q plus 2.5006 with these numbers, if you do the calculation numerically, you should be able to get this one. Okay, basically this one is in the form of omega 1 squared 0, 0 and omega 2 squared. Okay, this matrix, if I would plug in the number here, and that is this form. Okay, so in this way, let me rewrite here. So that becomes Q1 double dot plus omega 1 squared Q equal to 0. Q2 double dot plus omega 2 squared Q2 equal to 0. So here the omega 1 squared equal to 2.5, omega 2 squared equal to 6. So that is the information we copy from that one, from the symbolic to here. Okay? Everyone need to take a break for any questions? So probably that we can have a short break.